All right, welcome to module 3.2, where we're going to look at how you can actually draw atoms and represent atoms in different ways. You can see again our learning intentions and success criteria there on the screen. Feel free to pause the video and read them, but we're going to jump straight into it. So, as I mentioned in the other video, electrons are found in shells around the nucleus of an atom. Now, something you need to know about these shells is that they can only hold a specific number of atoms. Shell 1 can't hold more than 2 electrons. Shell 2 can't hold more than 8 electrons. Shell 3 can't hold more than 18, and shell 4 can't hold more than 32. There can be more shells than this, but we're going to stop here. Now, you might notice that it says KLM and N in brackets after those. They're just there because some places, instead of saying first, second, third, and fourth shells, they'll call them shell K, shell M, or shell N, or shell N. That's how they do it. But we're going to try and just stick with 1, 2, 3, and 4, and any numbers we need. So you can also see over there they've got an example of what we're talking about with calcium. Calcium has 20 electrons, and you can see how it's arranged, although you might notice that shell 3 doesn't actually have 18 electrons. Now you see, generally speaking, we fill up the shells one at a time, but there is a bit of an exception to that. So when we're looking at our first 20 atoms, and that's all that we're going to ask you to draw up to, would be just being able to draw any one of those first 20. Beyond that, things get a little bit tricky. But remember, shell 1 has a maximum of 2. And everything after that, when they're the outer shell, is only going to hold 8. The only way they can ever hold their full maximum is if they're no longer the outer shell. So if you're going along, and like I said on the slide before, you might notice that instead of holding 18 electrons like shell 3 has as its maximum, over here it actually only has 8. And that's because when it was the most outer far away shell, it couldn't hold more than 8. If it did, it wasn't going to be stable. And so it's not able to do that. So the way it gets around this is it quickly creates a new shell by having 2 more electrons in there. Once there are 2 electrons in a outer shell, it's established as the outer shell, and then the atom can come back and start backfilling. And that's what happens after the 20th atom, which is calcium. So generally speaking, shell 1 has a maximum of 2 electrons. And while a shell is the outermost shell, the maximum it's ever going to hold is 2. So once the shell is full, a new shell will be made and electrons are going to be placed in there. We'll look at silicon as an example. So silicon has 14 electrons. So we're going to put the first 2 are going to go in shell 1. Then we're going to put 8 into shell 2 because that's the most shell 2 can hold at all. And then we'll have 2 electrons left over. So we'll have 4 electrons left over. So we'll put those last 4 into the third shell. And that's what we've got in the diagram on the right. So here is that again. So you've got all your protons and neutrons are in the nucleus. You've got your first ring holding 2 electrons, no more than 2 for the first ring. Second ring can hold up to 8 electrons, no more than that. Third ring, remember, has a maximum of 18, but while it's the outermost shell, it won't hold more than 8. And fourth can hold up to 32, but again, if it's the outermost shell, it's not going to hold more than 8. So you need to create a shell after that and then come back and backfill it up. So let's have a look at what carbon looks like. You've got your nucleus there in the center. We just generally for this, which we call a Bohr model of the atom or a shell diagram, we just draw a circle for the nucleus. It's good practice also to write the symbol of the element you're talking about in there. This one doesn't have that. If it did, it would have a C in that blue circle. So you would know that there's going to be 6 protons and 6 neutrons living in that nucleus. So that's what we've got there. But around that, we've got our electrons, and those are the sort of magenta colored circles. And so we've got 6 protons, we must also have 6 electrons. So we're going to place 6 around it. So the first 2 out of those 6 are going to go in shell 1. And that's going to leave us with 4 electrons. And so we're able to put all those 4 into shell 2 quite happily. All right, so that's sort of the basics of it. Now, if you're like, oh, I'm never going to remember how many each shell can hold, well, there is a little bit of maths you can do. Now, it's actually pretty easy. We can use this equation, 2n squared, where n is the shell number. So what this means is that if you're talking about, let's say, we'll talk about the shell and the max electrons. If it's shell 1, 2, 3, or 4. What you would do is you would go and put the 1 into that equation where n is. So you go 1 squared then times that by 2. So 1 squared is 1, and then times 2 is 2. 2 squared is 4, times 2 is 8. So that would be for shell 2. Shell 3, 3 squared is 9. 9 times 2 is 18. And for 4, 4 squared is 16, and 16 times 2 is 32. So that's actually where those numbers, you can work them out mathematically if you can't remember them off the top of your head. And sometimes it's easier to just remember the equation than to remember the whole set of numbers. Now, you might have seen in a couple of other places that instead of always having shells, we have the way the electrons are set out in those shells. We just have them written as numbers. This is actually called the electronic configuration. And so it's just the distribution of electrons in their shells. And so you can see that down the bottom here for sodium. Okay, so what we've got, sodium has 11 electrons. You'll have 2 in shell 1, 8 in shell 2, and 1 in shell 3. And so we can actually just write it this way. It's much quicker. And you can even do this and then draw a shell diagram using that information, which is what we've done over on the right here. So you can see there's sodium there. All right. So like I was saying, some important rules. Shells are going to fill up one at a time, and you don't move on to the next shell until that shell is completely filled. Unless, and this is so important, unless in filling up that shell, you actually end up having more than 8 electrons. You're not allowed to do that. Once you get to that 8th electron in the outermost shell, you have to go and create a new shell to be the outermost shell or the valence shell. And you have to get 2 electrons in there. And once you do that, then you can come back and finish filling up the one beforehand. And then move on after that. When it comes to writing out things like shell diagrams, electronic configuration, you're only going to go up as high as calcium, which has an atomic number of 20, in which you would only go so far as to create a 4th shell and put 2 electrons in there. You won't be coming back and backfilling the 3rd shell with that. So over on the side here, what's probably most interesting is argon and potassium. So here we've got argon and potassium, Ar and K. Argon is 18, potassium is 19. So you've got 18 electrons, and we go 2, 8, 8. Makes perfect sense. This is where it comes into play. Because at the moment shell 3 is the last shell, it can't hold more than 8 electrons. Even though technically it's able to hold a maximum of 18, at this point in time it can't do that. It can only hold 8. So what potassium does is it goes and it puts 1 electron into shell 4. Calcium comes after potassium, and you'll see that calcium is 2, 8, 8, 2. And that's because that's putting in that second one into shell 4. Now it's fully established. What comes after calcium would talk about now filling up back here where you've got shell 3, and you can actually fill it all the way up to that maximum of 18. Now, to get a bit of a handle on this, there is an activity sheet for you to do. It looks a bit like this. So what you need to do is go through it, and you can see neon's been done for you. You don't have to draw dots. You can if you want. You can just draw X's to represent the electrons. If you're not sure how many electrons it should be, if you look in each one, you can use the periodic table and just find your atomic number. But the atomic number here is the bottom number out of the 2 that are in each section there. So you go through and do that, and then you've got the 3 questions to answer. What do you notice, first of all, about the elements in each group? What do they have in common? So groups are going top to bottom, so they're the columns. So that's going this way. And what about the periods? What do you notice about them? The periods are the rows, so they go that way. And then have a go at writing out the electronic structure for a sodium ion and one for a chloride ion. Hopefully you remember from last lesson what happens with ions where they gain and lose electrons. So give that a bit of a go. Alrighty, hopefully you've had a chance, you've paused the video and you've gone through that worksheet. We're going to go through that as quickly as we can now. I'm going to do a couple and then I'll go through doing the rest, and I'll speed up this next little section. But I'm going to show you calcium actually to begin with, so actually right down the bottom here. So you've got calcium, and calcium has 20, so we're going to go 1, 2, then we're going to go 1, 2, 3, 4, 5, 6, 7, 8. So far I've put 10 electrons in, because 2 then 8 is a total of 10. So I've got another 10 to find homes for. So I'm on to shell 3. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Now even though there's another circle drawn in, at the moment as I'm filling it up, shell 3 is the outermost one. So I can't actually add any more into it at this point in time, but I still have 2 electrons. So what I can do is I can put one here and another one here, and I now have 2 in that outer shell. So if I was going to continue on into where it says transition metals, which you do not have to do, and you don't have to do any of this at all, what would happen is I would then go back into shell 3 and start filling that up. But like I said, not something you actually have to practice, just be aware that that's where it's going. I'm also going to jump around and I will do carbon for you. So carbon has 6, so we've got 1 and 2 in the first shell, and you've got 1, 2, 3, 4, so 2 plus 4 is 6, and that would be carbon. All right, so I'm going to go through now and I'm going to start filling in the rest of them. Alrighty, so there we go. That's them all filled up there. Unfortunately, some of them got a little bit wonky towards the end, just running a bit out of space. But that is generally what it should look like. And you should see an increase of 1 electron or 1x each time you move along. Now, there were 3 questions for you to answer. First of all, what do you see in each group? What do you see as you're going down in these groups? What do you see that they have in common? All right. Hopefully you've had a look at yours and been able to realize that each group has the same number of electrons in the last shell. So group 1 here all have only 1 electron. Group 2, the second column, all have 2 electrons in that last shell. With boron and aluminium, they both have 3. Carbon and silicon both have 4. Nitrogen and phosphorus both have 5. Oxygen and sulfur both have 6. Fluorine and chlorine both have 7. Neon and argon both have 8. Helium only has 2. However, because helium only has 1 shell, and that's its maximum, what you're actually seeing there is that the shell is filled to its absolute maximum that it's able to have at that point. So that's what you actually see is elements in the same group will have the same number of valence electrons. What about the ones in each row or each period? Have a pause and have a look and see if you can work it out. Did you pick it up? Each row has the same number of shells. So row 1 or period 1 has 1 shell. Row 2 or period 2 has 2. 3 has 3 and 4 has 4. So that's what they've got in common there. Now, the last thing there wants you to draw and write out the electronic structure for sodium ion and a chloride ion. So just, if you don't know already, sodium as an ion is Na+, and chlorine as an ion is Cl-. So if you haven't done it already, pause the video and write those out now. Okay, so normally sodium has 11 electrons, but it's a plus, which means it's lost 1. So instead of 11, it's only going to have 10. So it's going to be 2 and then 8. Chlorine, on the other hand, chlorine normally has 17, but it's got a minus, which means it's gained 1, so it must have 18. So that would be 2, 8, 8. And that's all you have to do for that. So here's a couple of other ones to do and try and work out electronic configuration. You've got fluorine, magnesium, argon, and calcium. And you've got an example to the side there with sodium, oxygen, and silicon, just showing you what you sort of need to do and what's expected. So you want to work out, you've got in brackets there the number of electrons, then how would you actually put them into those shells? So pause the video and give that a bit of a go now. Okay, so let's start with fluorine. Fluorine has 9 electrons. We're going to put 2 in the first shell, and then that leaves us with 7, which we can put all of those in the second shell. All right, so that is fluorine. Magnesium, same deal, 2 in the first shell. We're left with 10, so we can put 8 out of that 10 into the second shell, but we can't put more than that. And now we're left with 2 more, but both of them can go into shell 3. All right, argon is similar to magnesium. It's going to go 2, 8, and then we're left with 8, and they can all fit into the third shell at this point. So we'll put them all in there. Calcium, building on what argon did, it's going to be 2, 8, and this is our third shell, and it's the last one, so it can only have 8 at the moment. And then we've still got 2 left, and those 2 go into shell 4. If it was after calcium, then you would come back to shell 3, but you need to have at least 2 in the last shell before you can do that. So that is what you would have. So we've been talking about how to arrange electrons and how to actually draw a shell diagram and how they fit into those shells. But how they fit in and the different number of shells we have and the different number of valence electrons you have is actually really, really important when it comes to the properties of the atom. So the atoms with the same number of valence or electrons in the outermost shell are actually going to share chemical properties. So for example, if they're in group 1, they have one valence electron and they actually all react in the same way to water. They burn and they sort of can even explode a little bit. So they behave in very similar fashions. So an elements group is the number of valence electrons. Now you can see there it says with some exceptions. There is a reason for this. What you find with the periodic table, so we'll just draw this. So this is just sort of the top of our periodic table. This is 1, this is 2, and then it actually goes down here 3 all the way to 12, and then you've got 13 all the way, this is 17, and that's 18. So this idea here works really nicely for groups 1 and 2. Okay, group 1 and 2, that's how many valence electrons you have. But it doesn't work for 3 through to 12. Okay, and that's because they're our funky group where you're going backwards and filling things up. What then happens for 13 through to 18 is it's the group number minus 10. So what that means is if it was 13, you go 13 minus 10 would be 3. So for example, group 13 has boron in it. And if you look at boron, boron has 3 valence electrons. And that's because that's that 13 minus 10 gives you 3. If you jump to the other end and you looked at, say, argon, argon is in group 18 and it has 8 valence electrons. So you can see 18 minus 10 gives you 8. So that is just something to be aware of, that it works really well, really, really, really well for groups 1 and 2, but not very well at all for 13 through to 17. You have to take that 10 off, and the rule doesn't work at all for 3 through to 12, which is what we would call the transition metals. We'll talk about them in a little bit later. But what does work really nicely every single time is you can work out how many shells you're going to have just by looking at the row it's in. So you can see there an elements row is the total number of shells. So it doesn't matter if it's in row 1, 2, 3, 4, 5, 6, 7, whatever the number is, that's how many shells it's going to have. So here is a bit of an example. Remember, groups are columns and periods are the rows. So the groups are the ones that go top to bottom, and the periods are the ones that go side to side. So looking at that, can you work out how many shells lithium has and how many valence electrons it has as well? Pause the video and write your answer down now. Okay, so in terms of how many shells it has, shells we look at the period. So it's in period 2, therefore it has 2 shells. Okay, now we gave you a nice easy one here for valence electrons. This is group, and it's in group 1, therefore it has 1 valence electron. Okay, so that's all you had to do. So lithium is 2 shells, but it only has 1 valence electron. And that's because lithium, if I just draw it here, this is lithium's nucleus, here's shell 1. Lithium has 3 electrons. It's got, we'll put one here, we'll put one here. Those are the first 2 in shell 1, and then when you do shell 2, the third one sits in there. So you can see it's only got 1 valence electron. So what I want you to try now is actually you've got something a bit different to do. Here's the electronic configuration. Can you name the atom? Can you work out what period it is and which group it's in? Now, I'm going to give you the heads up. That last one is very difficult to work out what group it's in. So see if you can give it a go, but don't be too upset or too frustrated if you can't. Like I said, that one just for working out the group is particularly tricky. You can work out the period nice and easy and name it as well, but working out the group is a little bit harder. But it's always good to test ourselves and see if we can learn something new. So pause the video now and give that question a go. Okay, so let's start with A. So A has a total of 7 electrons. So if I was to look at the periodic table, I'm looking for something number 7. So number 7 is nitrogen. Okay. To work out the period it's in, I need to know how many shells it is. So I have 2 sets of numbers. That means there are 2 shells. Therefore, it is in period 2. In terms of what group it's in, I want to know how many valence electrons it has. Now, that means I look at the last number. So here I can see 5 is my last number. So I'm looking for actually group 15, because remember, it works really nicely, just straight conversions for group 1 and 2. 3 through to 12 you ignore. So if you've got anything like 3 or higher, you actually want to add 10 onto that to get the group number. So that's actually going to be group 15. All right, so that is A. Now B. Similar thing, working out which element it is. I'm going to add them together. So I've got 13. So 13 electrons is going to mean 13 protons. So I'm going to look for number 13, and that happens to be aluminium. Its period is 3 because I can see my electrons are split into 3 groups. That must mean 3 shells. So period 3. And finally, I'm looking there, 3 is my last number. So again, like the other one, I'm going to add 10 onto that to get my group number. And that's going to be group 13. All right, now this last one, like I said, the first 2 parts are actually quite easy, same as the other one, but it is the last one that is the tricky part. So if I add all those together, 2 plus 8 plus 10 plus 2, I'm going to get 22. So I'm actually just looking for what's 22 on the periodic table, and that is titanium. And then again, I can do the same thing with the period. How many groups are my numbers split into? They're split into 4, so it must be in period 4. Now, this one's a bit funny because I can see it has 2 at the end, but it's actually not in group 2. And that's because if you look right before that, you'll notice that the third number is bigger than 8. And that tells me that it's already gone past calcium, calcium itself being in group 2. And it's gone and moved on from that by 2 spots. So it's actually in group 4. Okay, now, like I said, that was a tricky one. You won't be getting questions like that. That was just a bit of a test to see if anyone could work that out. If you did, great work. But if you didn't, again, don't stress about it. So we're going to move on and we're going to talk about electronic configuration of ions. Now, you actually had a question before about this, so you might already have worked this one out. But basically, you need to remember that ions are formed by gaining or losing electrons. So the electronic configuration of many ions is going to be that to the closest noble gas to them on the periodic table. Because remember, noble gases really, really stable. They're your group 18 elements. They've got those full outer shells. They're nice and happy, and they're nice and stable. So a lot of the time what we're seeing is elements are losing or gaining electrons because they're actually trying to get to that stable point. They'll either gain extra ones to work their way up to it, or they'll lose some so they can drop backwards a little bit down to the closest one. And so when you're writing the electron configuration of an ion, you need to take into account either the addition or loss of those electrons. So we actually did sodium before as well, but you can see there normally sodium has 11, but when it becomes an ion, it loses that very last one. And so instead of being 281, it's just 28. To that end, I want you to give this a go. Pause the video now and try and work out the electronic configuration for the following ions. Alrighty, how did you go with that? Let's dig into it. So we've got magnesium to start with. Now normally magnesium has 12, but it's got 2 plus, which means it's lost 2. So instead of 12, it's going to have 10, which is going to go to then 8. And that's it. That's all you need to do. Chlorine normally has 17, but it's got a minus, so it's gained 1. So that means it's going to have 18. So we're going to go 2, 8, 8. Oxygen is normally 8, so it's actually gained 2 from that. So 2 plus 8 is going to be 10. So we're going to draw that out. So we're going to go 2 and then 8. That gives us 10. And finally, beryllium. Beryllium is normally 4, but it's 2 plus, which means it has lost 2. So 4 take away 2 is just 2. That's all beryllium is, just 2. So that's it for that. And that's how you can write out the electronic configuration of different ions. All right, so I want to talk now about how you can also get electrons to move within an atom, not just moving out of an atom like they do with for ions, or moving into an atom from somewhere else. So electrons, remember, live in energy levels. That's what the shells are, they're energy levels. If you can get those electrons to absorb more energy, you can actually get them to shift into different shells. So if electrons actually absorb enough energy, they can move up shells. So that might be going from shell 3 to shell 4. However, when an electron does jump into that higher energy level or that higher shell, it's really unstable. We say it's in what we call an excited state. So because this isn't stable or sustainable, it doesn't actually stay there in the unstable state. And when it returns to its ground state, which is its original shell, it's got to get rid of that extra energy, and it emits it in the form of light. So what's really interesting about this is the energy difference between those shells actually determines the color of the light. So you can see there, you've got a Bunsen burner, but it's got a green flame, and that's because they're heating something in that flame, and it's absorbing the electrons are absorbing the energy. They're moving up the shell, but they're falling pretty well straight back down, and they're getting rid of the extra energy as colored light, and it happens to be green light that they're getting rid of it in. So that's really quite fun to do. This is basically what's happening. You have energy that gets absorbed by the electron, and it comes in here. And when it's absorbed that, it can't hang out in its normal spot that it would. So it then moves up a shell, and it moves to this higher energy level. But it's not sustainable. It can't stay there. So it's going to fall back down a shell, back down to where it originally came from, and it's going to hang back out there. But energy doesn't get destroyed, and it just doesn't vaporize. It has to be sent off, and it gets sent off or lost to the environment in the form of colored light. So energy gets emitted by the electron as colored light, which is very, very pretty. And it's the basis of how fireworks actually work. The reason you have different colored fireworks is because you have compounds in there. When the explosion happens and all the energy gets released, those compounds, those generally metal atoms, they absorb that energy, and their electrons move up, and then they move back down, and they release the extra energy as colored light. And that's where we see our pretty fireworks come from. We can also burn stuff in Bunsen burners, or you can set something in a flame like we've got in the picture here, and you can also get different colored light from that. So what we're talking about here and what we're doing with this is we might want to actually show someone this happening. Now, there's a number of ways that those electrons could move. So generally speaking, this is sort of just a very general way of representing it. You've got here your ground state. Ground state of sodium could be something like 281. Okay, now that's what sodium normally is. But when that last electron might absorb energy, it might move up to shell 4. So it might become 280, then 1. And that's how you would actually write it in the electronic configuration. You might have something where it actually turns into 272 because one from the third shell's moved up. Generally, you've got at least one moving up into a different configuration, so you might get something a bit weird, and that's a very unsustainable configuration. That's why it falls back to it where it would normally be, but that would be how you would write it. So have a bit of a go with silicon, see if you can come up with a way that it might have its electronic configuration. How did you go with that? Did you manage to come up with one? What you might have for silicon, you could have something along the lines, silicon normally has 14. So silicon normally is 14. Okay, so that would normally be 2, 8, and then 4. But when it gets excited, it might become 2, 8, 3, 1. It still has the 14 electrons, but now you can see one of them's actually moved up. So you might have represented it that way, but you could have done a whole different thing. You might have gone 2, 8, 2, 2. That would be just as correct for this scenario. So that's how we can actually show something getting excited with its electrons and moving them around like that. Now, just a bit of a recap and a refresher on some of the stuff we've been talking about. There's an interactivity online that you can go and complete. However, I want you to fill in this table down here. Now, some of the table it doesn't matter what you do, you're always going to get the same values in it. However, number of neutrons, whether it's stable or unstable, and what its mass number is can vary. So I'm going to come back in a tick and we'll go through some answers, but I'm going to highlight those ones that you might have gotten something different there, and that's totally fine as long as they all match up within themselves. But that's what that interactivity is for. It's about you trying things out and having a look at different forms of different atoms. So pause the video, go and do that interactivity, fill in the table best as you can, and then we'll come back and we'll go through it and we'll look at what some of the answers are and what some of the other ones might have been and that sort of thing. So just pause the video now and go and do that. Okay, so let's go through some answers. So I'm going to go through the ones that it doesn't matter what you did in the interactivity, you should have gotten these. So first of all, everyone should have gotten the same elements because we've all got the working from the same number of protons. So this is oxygen, oxygen again, then you've got neon, then boron, and finally hydrogen. Okay, you also can determine whether it's an atom or an ion. What you need to do there is look at the number of protons and number of electrons. If they're the same, it's an atom. So we can say that this first one is an atom. The next one is different, so it must be an ion. Neon, they're both the same, so atom. Boron, they're the same, atom. And finally hydrogen, they're different, so this is an ion. Okay, so everyone should have gotten that the same. The one other thing you should have gotten the same would be the atomic number. Now the atomic number and the number of protons are the same thing, so we can just take any number that's in the proton category and transfer that across. So this should go 8, 8, 10, 5, 1. So that's what you should have. Oh, sorry, the other thing you've got there is the net charge. The net charge should also be the same for everybody. So if you have an atom, your net charge is going to be 0. So we're going to put 0 in here, 0 in there, and 0 in there. Now, if it's an ion, you've got to look at the difference between protons and electrons. If you've got more electrons, it's going to be negative. So here for oxygen, I have 2 more electrons than I do protons. So I've got 2 more, and I've got electrons, so it's 2 more of negative charges, so 2 negative. For my hydrogen, I have 1 less electron, so it's 1 electron that's missing, and because it's missing, overall there's a greater positive charge, so that is actually 1 plus. Now, for these other 3 columns, the number of neutrons, whether it's stable or not, and its mass number, the last 2 are all tied to how many neutrons you have. So whether it's stable or not, and its mass number, all comes down to how many neutrons did you put in. So I'm going to fill in the values I grabbed. You might have done something different, that's fine, but this is what I did and how it came out for me. So I had 10, then 7, 10, 6, and 2. Now, this meant for oxygen, this first oxygen was stable, but this second one was unstable. For my neon was stable, so was boron, but my hydrogen was unstable with that number of neutrons. Finally, the way I get my mass number is I'm going to add the column with the protons and the neutrons together. So 8 plus 10 is 18, 8 plus 7 is 15. 10 plus 10 is 20, 5 plus 6 is 11, and 1 plus 2 is 3. So that's my table. Like I said, this column here, this one here, and this last one here, if you put in the same numbers, you should have gotten the same results for that first column with the neutrons and then the stable and unstable mass number. But if you did different numbers of neutrons, you're going to get different answers for the other ones, and that's totally fine. This was a bit of an activity just to get you to investigate things and how things change. This brings us to the end of the PowerPoint. I hope you have learnt a bit from it. If there's anything you're still uncertain of, you can go back, you can speed it up, slow it down, jump back to the bits you didn't get. And if you've got any questions, remember to ask your teacher for help and just for clarification from them. What you can do now is that last little activity down the bottom. It says to pick one of the 4 games. There's a tab at the bottom of the screen when you're on that website where it says games or symbol or atom, and then pick which game you're going to do and complete all 5 questions in that game. Just a bit of extra practice there. So go and do that now and have a bit of fun with it. But that's all, and thanks for watching the video.